Okay, so we are starting chapter 10, which is the last chapter for our class, but it's by far the longest chapter. There's 8 sections in chapter 10, and we're going to stretch these out from now until the end of the semester. So, chapter 10 can be kind of thought of as our applications chapter. We're looking at all sorts of different applications to the trigonometry that we've done up until this point. Section 10.1 and 10.2 are kind of like a part A and part B of sorts. They concern the same type of applications but using different perspectives. So to start with, in section 10.1, we're going to be working with non-right triangles. These are oftentimes called oblique triangles in many textbooks. And specifically, we're going to talk about something called the law of sines. So what we want to talk about here is trigonometry that's not restricted to just a right triangle or, I was going to say or the unit circle, but I actually don't want to say that. We're looking at triangles here, but there's no assumption that these are right triangles. They can be any kind of triangle. And I want to remind you of the convention that we use for notation. So in our book, we're going to label angles using Greek: alpha, beta, and gamma. We're going to label the sides of the triangle A, B, and C. Now the Greek letters alpha, beta, and gamma are the first 3 letters of the Greek alphabet. So it's kind of like A, B, and C, but in Greek. And you'll notice that the sides of the triangle that are opposite given angles have the same, let's say, letter of the alphabet, one in the Latin alphabet or English, one in Greek. So for example, alpha is opposite A, beta is opposite B, gamma is opposite C. It's important to know that convention because a lot of the work that we do in this section is going to ask you to work with triangles like this, where we give you some of the information. I give you, for example, what gamma is equal to, maybe A and maybe B. And it's up to you to find the remaining 3 pieces. But I won't draw the triangle. I'm just going to tell you A equals this, B equals this, gamma equals this. And you need to know that C is the side that should be opposite gamma, and so on and so forth. So make sure you understand this convention here. Now this part here that's labeled H is what we call an altitude for this triangle. So if we let side C be the base of this triangle, H is the altitude or height of that triangle. It's basically just a line segment that goes from the vertex up on top to the base so that it creates a right angle here. We're going to use this diagram to derive the law of sines. So the law of sines is a relationship between all 3 angles and all 3 sides of this general triangle. And what I'm going to do is start by taking a look at this first angle here, alpha. If I were to take sine of alpha, okay, notice that because this side H here has created these 2 right triangles within the non-right triangle that we're looking at, I can think of sine of alpha in terms of opposite over hypotenuse within this smaller right triangle right here. That would look like H over B. Okay, I'm going to do something similar with this other base angle right here, beta. If I took the sine of angle beta, I can use this other right triangle and say that it's equal to opposite over hypotenuse, or sine of beta is equal to H over A. Now what I'm going to do is take each of these equations, solve each one for H. Just multiply both sides of this by B, multiply both sides of this by A. So that's going to look like this. B sine of alpha equals H, and A sine of beta equals H. Okay, now the reason I did that is because I now have 2 different expressions that are equal to H. That means I could set these 2 expressions equal to each other, since they both equal the same thing. So I have B sine of alpha equals A sine of beta. And finally, what I'm going to do is take this equation and just represent it in a different form. So I'm going to take both sides of this equation and divide them by AB. Now in the first equation, the B's will cancel out. And in the second, the A's will cancel out. And what that leaves me with is sine of alpha over A equals sine of beta over B. Okay. Now, notice this equation doesn't include a gamma or a C anywhere. It's leaving out that third side and that third angle. But if I wanted to come up with a similar derivation where I'm including the C and the gamma in this somehow, all I would need to do is take this triangle and rotate it so that a different side is a base. I could maybe make A the base of this triangle, or B. And then I'd have to redraw the altitude and go through this derivation again, and I would get a very similar relationship. So if I include all the relationships I can get using a derivation like this, we get something called the law of sines. The law of sines says this: for any triangle, doesn't need to be a right triangle, but any triangle at all, where the angles and the sides are labeled the way that we did above, sine of alpha over A will equal sine of beta over B, which will also equal sine of gamma over C. And the way that we use the law of sines is, we use it for a number of things, but what we're going to primarily do here is use it to solve triangles. We've seen this term before, solving triangles, but what we mean by that is if I took this triangle here, there's 6 pieces of relevant information. There's the measures of the 3 sides and the measures of the 3 angles. In 10.1 and 10.2, the primary thing we're doing is you'll be given 3 out of those 6 pieces of information, and then you use the law of sines or other tools that we'll develop across this in section 10.2 to find the remaining 3 sides. So this law of sines gives us the relationships that we need in order to do that. Here it takes the reciprocal of each of those expressions, so it gives you just an alternative presentation for that. So let's take a look at the kinds of triangles that we can solve using the law of sines. There's 3 cases that we're going to encounter here. The first case is called ASA, which stands for angle side angle. And what that means is you're going to be working with a triangle where you have 2 angles and a side between them, or we sometimes call that the included side between those 2 angles. So that if you kind of work your way around this triangle, you know, like maybe in a counterclockwise fashion, you encounter an angle first and then a side and then an angle. So angle, side, angle. If I give you those 3 pieces of information, we can use the law of sines to find this 1 missing angle here and these 2 missing sides here. Then we have the AAS case, angle, angle, side. So that's where we have 2 angles and a non-included side. As I work my way from this angle around the triangle, I hit an angle that I know, followed by another angle that I know, followed by a side that I know. We can use the law of sines here to find the missing pieces of that triangle. The final case where the law of sines can be used is in the side-side angle case. That's where we have 2 sides and a non-included angle between them. An included angle would be the angle that joins these 2 sides, but we want one that's not included. So as you work your way around the triangle this way, side, side, angle. This is sometimes called the ambiguous case, and we're going to talk about why probably in the next video. This one, depending on the measurements that I'm giving you, can lead to an impossible case where there is no triangle that satisfies those measurements, a single solution, or there can be more than one solution. But we'll get into that in more depth after we've worked through a couple of examples. So let me start with this. I want to solve the triangle with the given measurements. Alpha equals 41 degrees, beta equals 77 degrees, A equals 74. If you look at what I'm given here, this would be, if you kind of look at the different cases up here, this would be an angle side angle kind of a case, because I'm given alpha and beta, and I'm also given side A. I'm sorry, I said the wrong one. It's AAS, angle, angle, side. Remember, side A would be the side that's opposite angle alpha. And if I know alpha, beta, and gamma, and alpha, beta, and A, that's angle side. Sorry, I pointed towards the wrong thing initially there. So I can use the law of sines to solve this triangle. What I need to do is find the missing pieces. So one thing I can find really quickly is gamma. Remember, gamma is the one missing angle in this triangle. And I know that all three angles in any triangle have to add up to 180 degrees. So if I know two of them, then I really know the third as well. I just need to do 180 minus the 41 degrees for alpha minus the 77 degrees for beta. In this case, I end up with 62 degrees for gamma. Okay. Now I need to find some sides. So I have side A, but I'm missing side B and side C. I'm going to start by finding side B. I can do that with my law of sines. So the case I want to use for law of sines is sine of alpha over A equals sine of beta over B. Okay, that's four things that I need: alpha, beta, A, and B. I have three of them. That means I can use those givens as well as just a little algebra to solve for the one piece of that I don't know. So sine of alpha. Alpha is 41 degrees. That means I'm looking at sine of 41 degrees over A, which is 74. So that's 74. And we set that equal to sine of beta, which is 77 degrees. Sine of 77 degrees. And that's over B, which we don't know yet. Okay? Now what I'm going to do is cross multiply to solve. So this is going to be B times sine of 41. And this will be 74 times sine of 77 degrees. It's important that you don't start plugging things into a calculator quite yet. We are going to use a calculator for this, but we're going to save this until the very last step. And I've addressed this before. If you start punching things into a calculator too early, your calculator is going to round these values. And then every time you use a rounded value in a further step in that problem, you're introducing what's called compounding rounding error. The answer becomes less and less accurate every time you use a rounded result in a step in your process. So we're going to keep everything the way it's written until I have to plug something into a calculator. Notice here, to solve for B, I would divide both sides by the sine of 41 degrees. So B is equal to 74 times sine of 77 degrees over sine of 41 degrees. This is the point where I would want to plug that into a calculator. Make sure you're if you're using a scientific calculator, make sure you're being careful with how you place parentheses and things inside this expression so that your calculator is doing the correct order of operations here. If we plug this into a calculator, we should get a value that's approximately equal to 109.9. That's B. Okay, how then do we get C? Well, C is the same idea, except instead of setting sine of alpha over A equal to sine of beta over B, I would set sine of alpha over A equal to sine of gamma over C, because that's the part of the law of sines that includes the side C. Okay, and again, this is just a matter of plugging in what we know. So sine of 41 degrees over 74, again, which is equal to sine of gamma, which we just found a minute ago to be 62 degrees. So this becomes 62 degrees here, over C. Now I'm going to skip a step here because you may notice something kind of useful. When you're doing a cross multiplication problem like this, and the C is the thing that I'm trying to find, we can actually just multiply the two known quantities that are diagonal from each other. So I don't know C, that means I'm not talking about this diagonal, but I do know the 74 and the 62 degrees. These are known quantities. I can multiply those. 74 sine of 62 degrees, and then just divide by the one remaining known quantity, which is sine of 41 degrees. That's exactly what ended up happening up here. 74 times sine of 77. I multiplied the two known quantities, see that here, and divided by the one remaining known quantity, sine of 41 degrees. That's a shortcut that gets us through these a little bit faster. This can go into a calculator, and this one comes out to approximately 99.6. And at this point, we would say that we've solved the triangle because we found the three missing sides, or three missing pieces, one angle and two sides in this case. I'm going to do the next example in the next video. But before I do that, I want to point something out. With the chapter 10, and more specifically sections 10.1 and 10.2, we spend a lot of time working with angles that are in degrees. This is kind of a shift from what we've been doing up until this point. Even though we have worked with degrees, most of the angles we've worked with in this class have been in radians. But in chapter 10, we're going to be seeing more with degrees for several of the sections. Just wanted to throw that out there, just in case you're wondering, how come we're doing so much with degrees all of a sudden? Okay, I'm going to go ahead and do the next example in the next video.